Marzyeh, can you hear us?
I can hear you.
Hi, Marzyeh. Okay, and is the mic okay? Okay, awesome, great. Okay, thank you so much for joining us today, Marzyeh. So Marzyeh is an associate professor at MIT in ECS, where she leads the Healthy ML group. And her group focuses on creating and applying machine learning to understand and improve health in ways that are robust, private, and fair. So thank you so much, Marzyeh, for calling in, and we're looking forward to a talk. Thank you.
Hi, everyone. I'm really sorry I'm not there. I have whatever horrible flu has destroyed half of the East Coast. And so I'm sick and unable to attend, but I'll say hi virtually. And I'm going to go through this, I promise, at pace so that you don't miss your lunch. So I'm going to talk today about two projects. One is work that just came out in NeurIPS, and the other is work that we're planning to submit soon. And the backdrop for this is I think a lot about deploying models in healthcare settings where models have been established as really performance advice givers across a range of medical, discriminative, and generative tasks. But we really have limited evaluations of even FDA-approved models. And so there's this really nice paper that came out in 2022 that just looked at the set of FDA-approved AI tools at the time, and they found that only one was trained or validated using demographically representative US data. The average validation size was very small. I think you all agree 300 is very small for something that's going to be deployed in the wild. Most of these devices are assessed using only retrospective studies. And importantly, most devices, and when I say devices here, it's not a device, it's sort of this AI as a device designation. These models are not being assessed in a multi-center setting, right? So it's like one hospital, let me hold some data out and like test it on this unseen data. So the two things that I want to talk about today are, do we think model performance really can ordinally generalize in new settings? And we know that when we take a model and we apply it to new data, it's not going to do as well. And that's very well established. I'm not worried about that. I'm worried about whether the order is going to swap. So is the best model in my, sort of offline training set that I have here going to be the best model in a new setting? And how different could it be? And the second thing is whether we can use models to estimate what data might be most useful to them. So this should hopefully be obvious to everyone, but we know at this point that shortcuts tend to be bad for robustness. This is true in general, also in a medical setting. We have some work from a while ago where we looked at how obvious invisible demographic features are to AI models. So human doctors cannot look at a progress note like this and extract self-reported race, but AI models can with very high performance. Human doctors cannot look at radiology images like this and extract, again, self-reported race or other demographics, but models can. And so we had a paper last, I guess it's 2026, 2 years ago, so in 2024, where we wanted to look at whether spurious correlations were really damaging state-of-the-art models in medical imaging at the time. And so what we looked at was these three different settings, radiological settings, ophthalmological settings, and dermatological settings. And in each of these cases, it makes sense because people use images to decide whether a mole is cancerous or not, whether you have retinopathy or not, whether your chest X-ray has pneumothorax, cardiomegaly, no finding, you're healthy, right? So you have these tasks. And so in each of these settings, people have proposed models to look at some sort of image and then make some sort of risk predictor. And so we wanted to take state-of-the-art trained models and test two things. How much encoding of demographic information happens when it's not your intent, when you're optimizing the models to predict the disease class, and then you chop the head off at the end and then force a prediction in the with the final layer to predict some demographic. How well can you do that? And then secondly, how does that affect model generalization? And we did this across these three different attributes, sex, age, and race, because they're what we had available, and then intersectional sex and race in a couple of cases. And what we found is that when you train dense net models with empirical risk minimization, and they do really well, they get state-of-the-art performance on predicting the actual disease. They also encode demographic attributes. And this should not be a surprise. This is reasonably well established. We just wanted to make sure that it was also true in this case. What we also found, and what is new, was that greater encoding of those demographics is correlated with a larger disparity for those attributes. Put another way, the more I know who is male and who is female when I'm predicting retinopathy from an ophthalmological image, the worse I do at predicting retinopathy in female patients. Those two things tend to be correlated in the models that we trained. And there are ways to address this, right? So we have lots of group adversarial and subgroup robustness methods that we can use as optimizers instead of empirical risk minimization. So this is a Pareto plot that we were, told by several economists we had to include. So we did, where we have the overall AUC of any model. Every dot on this plot is a model. And then the y-axis is the fairness gap that model has between any two groups. And here it's across patients of different ages. So you can see ERM models tend to cluster in the upper right-hand corner, which makes sense. They have very high average performance. That's what you're optimizing for, but they tend to have very large fairness gaps, over 20% in this case between old and young patients. But nicely, right, very happily, you can just go down this Pareto plot and choose a model on the front down here that has approximately the same overall performance if you use group DRO, for example, to optimize. And the fairness gap is 5%, which we would say is honestly within label error within most of the medical data sets that we have. And this is not just true in this case, this is true in all these cases. So that was good news. But then there was this final bad news that sort of sets up the 2025 NERVS paper that we did, which is, well, what about in new settings? Because it's not like every hospital is sitting there training an optimal model with a Pareto front on just their data. What happens is Mass General is huge, has this sort of academic medical center, 11 different sites that it can draw data from. They optimize the model and then they throw it, the best model, to their friends at Stanford. And so that's what we did. We took this model, the set of models that are optimal in Massachusetts on the MIMIC data set, and then we evaluated them on the Stanford chest X-ray data set. What you can see is that Pareto optimality doesn't hold, right? So when you shift, there's this idea that you have performance in some ordinal way. Of course, when you move from one place to a new place, the model doesn't do as well, but we sort of expect things will move in the same order, and that's not true. Which set us up for this evaluation of how well we think model performance can actually ordinally generalize in new settings. And this is work done by my former postdoc Olawale Salahuddin, who's on the job market and is amazing. He's wonderful. And so his hypothesis was that natural data sets have enough sufficient spurious correlation to remove any sort of accuracy on the line performance in a new setting, in an out of distribution setting. And so accuracy on the line is this, sort of previously well-established thing that if you have a set of models that do well in some training setting, when you move to a new test setting that is out of distribution in some way, they will do more poorly, obviously, but they'll do more poorly sort of in a line. They'll sort of shift ordinally, right? So the best is still approximately the best and the worst is still approximately the worst. And so the setup that he used, anchoring back to this, chest X-ray example, is let's say that I have 4 different sites that I'm allowed to train on from 4 different countries. And then I have this out of distribution test set, right? All of chest X-ray data. And I'm trying to predict that a person is healthy. They have no finding. Well, what I would expect is that I could, take the models that are best in distribution and they would also be good out of distribution and there would be this correlation. And so, what? Guys. Okay. This is like the universe being cruel to me. Like, I'm already sick. I don't need this. Let's see if this works. Okay. You're going to see that this is in Firefox. I'm going to exit out of full screen just for this so that it's actually visible because for some reason the slide will not load. Okay. So how are we supposed to find these out of distribution subsets? Here is the classic algorithm box that we all know and love. What we're going to do is we're going to train a group of models. Okay, and we're going to build up a matrix essentially. So we're going to have a vector of accuracies in distribution. So if I have model 1 through model n, I'm going to build up this vector of how well a model is doing in distribution. And then I'm going to create a binary matrix that essentially is counting when out of distribution samples that I'm evaluating on, right? So I've trained on all this data from all these countries, and now I have this out of distribution Massachusetts test set. I'm just going to code it as a 0 or a 1, depending on whether it does correctly in this new out of distribution sample. Okay. And now I'm going to have a per model average accuracy vector across these samples selected by S, where S is constrained to be the size that I want for my out of distribution set. And I'm going to select them by optimizing this specific constrained objective. And this is going to select S out of distribution examples. And in practice, S is going to be the output of some sigmoid function. And our objective here is really to find the examples that are going to be out of distribution most often, even though you're doing really well in distribution. I'm just going to test and see if I can slideshow again. This is so weird. Oh, okay. Well, here you go. It's back. All right. So functionally, what's happening here is we want to identify data subsets where accuracy is negatively correlated with in-distribution accuracy, right? So nothing too crazy or fancy. And what we find, the interesting thing is, I would have assumed, and Wally asked me previously, he said, how big do you think these are? I would have assumed that these would be small data sets, right? That if you have, large numbers of in-distribution data sets and you're dealing with relatively large samples and state-of-the-art models, that you would not be able to select large subsets of data that exhibit accuracy on the inverse line, where the best model in distribution is the worst model on out of distribution examples. Like the number of examples in that out of distribution set should be relatively small in my mind. But it turns out it's not. And so in our chest X-ray example, what we found is up to 70% of the patients in the data set, so this is like 50,000 chest X-rays in the Mimic CXR data set, exhibit accuracy on the inverse line behavior. What that means is, I will walk through this plot briefly. Okay, so this is the correlation, right? And if it's in this sort of middle yellow band, that means there's only a weak correlation between how well this model does in distribution and out of distribution. If it's red, that means there's accuracy on the inverse line. If it's green, that means that you have accuracy on the line, meaning the best models in distribution are also the best models out of distribution. And this is the constrained size of S, how large of a set of examples we're allowing our OOD select algorithm to choose from. And so this side of the graph probably intuitively makes sense. If you only allow the model to choose 1% of the examples, well, I can pick examples probably in any data set as long as you make the set size so small such that I'll get accuracy on the inverse line behavior, where the best model in your data setting is suddenly the worst in my data setting. But I certainly didn't expect that you'd be able to select such a large proportion of the data set and still have accuracy on the inverse line behavior. And just to clarify, because this is what I thought initially, these are not the most misclassified examples. If you instead look at just the most misclassified examples every time within the data setting, those are not, they don't have the same accuracy on the inverse line behavior. It's not like the best is the worst in the model transfer. And if you look at a baseline at just selecting for the same sample size between 1% to 100% random data sets from the out of distribution setting, you can see here that does exhibit accuracy on the line behavior, which is what we would expect. That's what most papers demonstrate. And then Right. And so this is not just true in the chest X-ray setting. The Wilds data set is an amazing data resource that hopefully everybody has used at this point, that across a large number of interesting human settings has diverse out of distribution test sets, and then in distribution training sets. And you can see that accuracy on the line versus accuracy on the inverse line behavior is very data set specific. So in some of these data sets, you very quickly cannot get accuracy on the inverse line behavior, for example, here in PACS, right? But in some data sets, again, as we saw in the chest X-ray example, and then also in civil comments, you can get very large data subsets that have accuracy on the inverse line behavior. And there are some things that seem to be sort of similar within some of the examples, at least the ones that are natural images and visually we can look through. But again, like there's nothing that is consistent that we could find that ties all of these examples together. So that's what we're working on now. Any questions on that before maybe hold questions to the end. I'll go through this this next part a little bit more quickly. All right. So maybe models can't always work so well in new data settings, but we also have some models, when we're not thinking about sort of this discriminative classification setting of trying to, predict something specific. We have models that are being used in generative settings in healthcare specifically, pretty widely, right? Where now it's pretty common to have an LLM in a healthcare setting and give it different information. So here, the history of prior illness, HPI. This is a paper from Nature Medicine 2 years ago now, but end of 2024. Where they looked at diagnostic accuracy of the model in these different models in these different cases, and they were looking at what happens when you add more data. And this is not specific to this paper. I just thought this was a nice figure showing a thing that is widely believed, which is all of these LLMs that are now deployed in healthcare settings, just give them all the data about the person and they'll do better and better, right? And they're good sort of digital assistants for healthcare providers. And so I have a starting postdoc in my lab, Yuxing Hao, who was previously at Cornell, who wanted to look at just sort of pick at this a little bit more. And she has a slightly more HCI background than most of the people in my lab. And so she was really interested in this, and I told her she should give it a try. So this is work she's in progress on. So let's say that you have a patient profile. There's a bunch of sentences. If you've ever looked at your medical record, it's just somebody writing sentences about you and then vitals or labs. And then in modern machine learning, LLM style benchmark data sets, what happens is you have data like this, a patient profile, and then you have a question answering sort of prompt for the model, right? So it'll say, what is the diagnosis for this person? And then the model has to choose A, B, C, or D. And what we wanted to look at is whether models and physicians would agree on what the relevant information in these histories are and how that would affect downstream task performance. So we looked at 4 of the sort of more popular common medical Q&A data sets, which have a profile of some kind with sentences, and then there's a question and there's an answer. And we recruited physicians and had them answer the questions and recorded how accurate they were, and then also which sentences they thought were most important. And we looked at 4 different language models, and same thing. Which sentences are the most relevant, and then which diagnosis is correct. And what we really wanted to look at here is in this, superset, now that we've glommed all these questions together in the evaluation, in this superset of 1,300 Q&A pairs, where we have both the answer that physician trainees think is true and the answer that LLMs think is true. And then we also have this sentence level relevancy estimated either using context site or self-reported prompting for the LLMs. And then we explicitly ask the humans to label it. How do these concord? Are they the same? How does this work? And so what we found is when we're comparing these 4 different data sets, and so there's the original, there's the physician trainee annotations, and And then again, we're getting importance either using the context site annotations or an LLM self-report. What we found is first, humans and LLMs tend to disagree a lot on information relevance. So there's very poor concordance between what LLMs think is relevant and what humans think is relevant. The closest one was Llama 70 billion, but even that was not that close. What's interesting to me is that human relevance, what I mean by that is if you remove everything in the data item, in the patient profile, except what the human says is relevant, so you only use the things that humans have labeled as relevant, that actually improves both human and LLM performance. So if I take like this long medical record that has lots of relevant and irrelevant information, and I give it to a human and have one human annotate what is relevant here, and then you feed only the relevant sentences in, that consistently improves both model performance across data sets and models and human performance, which is interesting. It's not something that we thought would be true previously. We also noted that, maybe this is not shocking, but GPT-4o, and this was done last year, and we're repeating now with GPT-5. GPT-4o actually performs relatively similarly to humans, right? So it's a pretty good model, and it's pretty close, except in a couple examples. And so we wanted to look a little bit more carefully within a model, GPT-4o, and say, okay, this is the model that's sort of doing best amongst the models at downstream accuracy in this Q&A task. And we see that human annotation of relevance improves task performance a lot. Oh, guys, like, right. Okay. So we wanted to look at what would happen. I don't know if any of you are, what is that word? Superstitious, but I swear somebody put like a hex on me. That's what I'm going with for today.
Yeah. We have around 5 minutes.
Yes.
Yes. Okay.
I'm about to close. So we then checked how well models do when we give them not just human annotations of what's relevant, but other model or your own model's annotation of what's relevant. And you can see in general, human annotations of relevance do best. They're sometimes matched by either GPT-4o in this case, or in this specific data set, the other two models do pretty well. And so this is something that we're looking at further. To summarize, I'll summarize very quickly, and then we can ask questions. For the first section, can model performance ordinarily generalize in new settings? Not really, under most real settings. There is enough of we know ERM doesn't work when we have spurious correlations because you can anchor to these shortcuts. And real world settings in real data sets have enough of this spurious correlations that we just aren't aware of in general, that they really fail to generalize, even if they're very, very performant, state-of-the-art models. They don't tend to do well in new settings, and you can choose very large amounts of the data and still get accuracy on the inverse line performance at deployment. And we're working to establish why some of these pieces of data, so individual data elements like specific patients' records or specific animals or specific pathology slides, are consistently accuracy on the inverse line. Because again, these are not the most difficult examples in all cases. There's something that seems to make certain examples difficult to generalize to, even if you're optimal in other settings. And there are spurious correlations that just aren't well known in those data settings. The second thing for the relevancy estimation is, models can sometimes estimate what data is going to be most relevant in the medical record, but not always. And humans are often better. And so right now we're investigating the gaps that we see in the estimations of relevancy and whether there are spurious correlations in what the models are consistently estimating as relevant and useful in their downstream performance for classification, but would not, again, generalize if we were in a real setting deploying these LLMs in the wild and expecting them to be able to generalize to a new patient population. And that's it. Thank you very much.
Thank you. Thanks so much. Yeah, so we have time to take maybe one or two questions. Any questions? Oh, yeah. Deb.
Can you hear me or?
Yeah,
I can hear you.
Yeah, sorry about the hex. But I was gonna say, how is it possible that with only so if 70% of the data leads to like an anti-correlation in terms of the ranking of the models, the remaining 30%, is it so strongly correlated with sort of the in-distribution ranking of the models that it flips it to be on the line? Like, how is that possible?
Yeah.
Is that what's happening? Yeah.
So
Yeah.
what's happening is you can choose subsets, very large subsets of this new data set, such that because you don't often evaluate on the entire data set, right?
Yeah.
Like when you're testing, right?
Yeah,
You're not
for sure.
testing on all of Mimic, for example, right? And so it's saying even if you took a really large chunk of Mimic to test on, 30% of Mimic, that's pretty big, right? You would still have like some performance that would say, oh yeah, this is accuracy on the line, this is really good. But in reality, you can choose like this other 70% and it would do really poorly. And again, that varies by task,
I see.
right? And it varies also by what features you include in the model, right? And so depending on what you're predicting.
So when you were showing the diagram where it was going from 0 to 100%,
Yes.
I was assuming that you were saying if you sub-selected the sort of most out of distribution examples all the way to like 70% of the examples, then the ranking of the models would be anti-correlated and you'd get this like sort of accuracy on the inverse line phenomenon. But then once you
Yeah.
add the remaining 30% that you've held out previously,
I see.
that it suddenly goes on the line. And I'm saying, are those 30% of examples so?
No.
Okay.
No. Yeah.
Yeah.
No.
So what's happening at the tail end there when it
Yeah.
shoots up into green?
Yeah. That's when you have to include everything, right? So
Yeah.
that's why as soon as you get here, you don't have accuracy on the inverse line anymore, right? Because now you've started to add in these other examples and the spurious correlation is broken.
Oh, I see. Interesting. So the additional 30, like the last 30% are sort of the examples that are most representative of the actual items or most correlated in terms of their representation with the in-distribution models.
They're the ones that are most correlated with the in-distribution models.
Okay, that's interesting. Thank you.
Any more questions? Okay, we can take one more.
Yeah, so
Can you hear? Project your voice. Yeah, thank you.
for the second paper that you were presenting, did you have a chance to look at the failure cases between humans and generative models? So you said that.
I'm so sorry. I can't hear you.
I think he's asking about failure cases between humans and generative models.
Yeah, thanks for the presentation. So for the second paper that you were presenting, you said that the generative models and humans had similar performance on a lot of the kind of like going through the diagnosis. Have you looked into the failure cases where if humans like failed in some cases that generative models did better or vice versa?
Yeah, so there's a couple of examples that it's very odd. Like humans get them consistently wrong, and models get them consistently right, or vice versa. There's one example where, and I can't remember which data set it's from, but in the data set, it's a patient and they're having consistent lower back. The first sentence is, patient has had consistent lower back pain for the past, 6 months or something like this. And then there's another sentence, and then another sentence, which is, pain is localized to that area only and does not radiate out. Like it's not affecting other areas. Models will get the answer to that question wrong unless if the cases look like this, right? Model, the question, sentence number 1 is this person has had consistent lower back pain for the past 6 months. And then there's 2 other sentences, and there's another sentence that says it's localized, it doesn't radiate out. If you remove that sentence, humans still do just as well. They get the case right, and they think it's irrelevant. If you remove that sentence, models think it's highly relevant, and if you remove it, they get the answer wrong. And so, we can hypothesize about why. It could be that implicit in the first sentence to any human clinician, if you are saying that it is lower back pain and it's been consistent for 6 months, implicit in that statement is the fact that it must not be radiating out. It must be localized to the region you just stated. if it's been happening for 6 months, it must not be like spreading, right? But that's not clear, or that direct clarification is needed in some way in order to align back to the correct answer for the model. And so we have examples like that, but it's difficult to understand why that's happening in general.
Got it. Thanks.
Thanks.
Okay, thank you so much, Marzyeh. Yeah, another round of applause. And so we can break for lunch, and then we'll return at 2 p.m. for more talks and a panel. Okay, great.